Today we're diving into a paper that explores the use of inverse reinforcement learning, IRL, for fine-tuning large language models, LLMs. The paper argues that IRL can be a more effective approach than traditional maximum likelihood estimation, MLE, for imitation learning in this context. What are the key challenges that MLE faces when applied to LLMs?
MLE, while simple and scalable, struggles with the sequential nature of language generation. It optimizes for individual token likelihoods, neglecting the impact of each token on the entire sequence. This can lead to compounding errors, where the model's own generations deviate from the training distribution, especially for longer sequences. Additionally, MLE doesn't explicitly consider diversity in generated outputs, which is crucial for tasks like creative writing or dialogue generation.
So how does IRL address these limitations?
IRL takes a more holistic approach by extracting reward functions from expert demonstrations and directly optimizing sequences instead of individual tokens. This allows the model to learn the underlying preferences and constraints of the expert, leading to more coherent and diverse generations.
Can you elaborate on how IRL extracts these reward functions?
The paper focuses on a specific IRL algorithm called IQ-Learn, which reformulates inverse soft Q learning as a temporal difference regularized extension of MLE. This means that IQ-Learn essentially performs MLE with an added regularization term that encourages the model to learn a value function that reflects the quality of generated sequences. The reward function is then implicitly learned through this value function.
That's interesting. So IQ-Learn is essentially a principled way to bridge the gap between MLE and IRL. What are the practical benefits of using IQ-Learn for fine-tuning LLMs?
The paper demonstrates that IQ-Learn can achieve comparable or even better task performance than MLE, while simultaneously improving the diversity of generated outputs. This is particularly evident in tasks that require reasoning or creativity, where the model needs to explore a wider range of possibilities.
The paper also explores both offline and online versions of IQ-Learn. What are the trade-offs between these two approaches?
Offline IQ-Learn is computationally cheaper as it doesn't require online rollouts, which can be slow and resource intensive. However, online IQ-Learn can potentially learn more nuanced reward functions by observing the model's own generations and receiving feedback from the expert. The paper finds that offline IQ-Learn already provides significant benefits in terms of diversity and performance, suggesting that online training might not be necessary in all cases.
The paper also analyzes the reward functions extracted by IQ-Learn. What insights did they gain from this analysis?
The analysis shows that IQ-Learn extracted rewards are strongly correlated with task-specific performance metrics, indicating that the algorithm is effectively capturing the underlying quality of generated sequences. This suggests that IRL could be a valuable tool for obtaining more robust and informative reward functions for use in subsequent RLHF stages, where the model is further fine-tuned based on human feedback.
That's a promising finding. So IRL could potentially be integrated into the entire LLM training pipeline, from supervised fine-tuning to RLHF. What are the key takeaways from this paper?
The paper demonstrates that IRL, particularly IQ-Learn, offers a scalable and effective alternative to MLE for fine-tuning LLMs. It achieves comparable or better task performance while promoting diversity in generated outputs. The paper also highlights the potential of IRL for extracting informative reward functions that can be used in later stages of LLM training.
The paper mentions that IRL can be particularly beneficial for tasks that require reasoning or creativity. Can you elaborate on why this is the case?
Reasoning and creativity often involve exploring a wider range of possibilities and generating outputs that are not simply the most likely or predictable. IRL, by explicitly optimizing for diversity and learning reward functions that reflect the desired qualities of these tasks, can help the model generate more creative and insightful responses.
The paper also mentions that IRL can be used to mitigate the compounding errors that can occur with MLE. Can you explain how this works?
By learning a reward function that reflects the desired behavior, IRL can guide the model towards generating sequences that are more consistent with the expert demonstrations. This helps to prevent the model from drifting away from the training distribution and accumulating errors over time.
The paper focuses on IQ-learn, but other IRL algorithms exist. Do you think these algorithms could also be beneficial for fine-tuning LLMs?
Yes, other IRL algorithms, such as GAL, could also be explored for fine-tuning LLMs. However, GAL is known to be more challenging to stabilize and requires careful tuning. The paper's focus on IQ-learn is justified by its simplicity, scalability, and strong performance.
The paper mentions that IRL could be used for pre-training LLMs. What are the potential benefits of using IRL in this context?
IRL could potentially be used to improve the quality and diversity of pre-training data, which could lead to better generalization and performance in downstream tasks. However, this would require significant research and development, as pre-training datasets are typically very large and diverse.
The paper highlights the potential of IRL for extracting reward functions that can be used in RLHF. What are the implications of this for the future of LLM training?
This suggests that IRL could play a more central role in the LLM training pipeline, providing a bridge between supervised learning and reinforcement learning from human feedback. By leveraging IRL to extract informative reward functions from expert demonstrations, we can potentially accelerate the alignment of LLMs with human preferences and create more capable and reliable AI systems.
This was a fascinating discussion on the potential of IRL for fine-tuning LLMs. Thank you for sharing your insights.